Hi everyone. Today we're going to be looking at the PLC Learning Series, Understanding Numbering Values. Now all programmable logic controllers, or PLCs, have the same numbering system at its core. This is the same with all computers as well. The status of the memory location can be either an on or an off. A 1 will represent the on or true status, and a 0 will represent an off or false status. This is called binary. Now we will be looking at how numbering systems work and some of the common systems that programmable logic controllers use. So let's get started. Detailed information contained in this video can be found at accautomation.ca. A link has been put in the description below. If you have not watched the other videos yet, there'll be links in the description below that will start you at video 1. There will be links to the rest of the videos in this series as well. So numbering systems use different base numbers, or number of bases. Now the number base indicates how many different digits are available when using a particular numbering system. For example, decimal is number base 10, which means it uses 10 digits, 0 through 9. We use number base 10, whereas PLCs, or computers, use binary. Now let's look at an example using a number-based system, a decimal numbering-based system, to figure out how we get this number. So the number is 3,527. So this is actually equal to the 7 digit here, 7, because that's the value, 7 of them, times 10, which is the number of digits, to the 0, which means the placeholder. So this is 0, 1, 2, and 3. So which equals 0. Any number or any base unit to 0 always equals to 1, and that equals 7, plus 2 times 10 to the 1, which is 2 times 10 equals 20, and then you have 5 times 2 to the 2, which is 5 times 100, which is 500, and then we have 3 times 10 to the 3rd, which is 3 times 1000, which is 3000. We add up 3,520 and 7, and we get 3,527. So we basically proved how we calculate that number to get the value that we do have. And we're actually converting it from decimal to decimal, but you understand how we actually get that value. Okay. And each of those positions that we see is called positional notation. And if you look that up, you'll actually see in our links below how that actually gets derived. Next, if we take a number like binary, and binary can represent numbers itself. So a single binary number is either 1 or 0, like we said, but combining these binary numbers together, we can form a value. And using the positional notation system, we can determine this value by the combined binary number. So if we look at 1111 in binary, and typically a binary, you'd always put a 2 down here in the right-hand corner. But that's the general way of writing the binary. So that's equal to 1 times 2 to the 0, which again is the placeholder, plus 1 times 2 to the 1, plus 1 times 2 squared, plus 1 times 2 cubed. And so that equals 1 times 1 is 1, 1 times 2 is 2, 1 times 4 is 4, and 1 times 8 is 8. We add those up and we get a maximum value of 15. So that is how our binary is actually working. This means that we can combine the 4 binary wires or switches together and have a maximum value of 15. If we include all the inputs, including the part where it's 0, 0, 0, then we'll have 16 possible combinations. So that's binary. So if we take the binary and we can actually take the binary number and we take a long binary number like this, 0, 1, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 0, 0, 1, 0. If we split that up into 4 different bits or binary, then what we can do is we can try to create a number system to represent this binary number, because this looks very hard to understand or helps to quickly look at it and calculate. So in order to do that, what we do is we switch to hexadecimal numbers. And hexadecimal numbers will contain 16 different symbols. So the first 4 bits of this symbol is equal to 11. The next one is equal to 1. And the next one equals 14. And the final one is 15, which is all ones. So that makes sense that that's going to be equal to that. So if we look at how we get this, if we look at the hexadecimal, again, it will have a base of 16 because we have 16 different symbols. We have 0 to 9, which is our standard, like decimal. Then we have to add another 5 or 6 locations to that, which is A to F. So A representing 10, B 11, C 12, D 13, E 14, and F is 15, which is the maximum value that we just calculated. So if we take that original binary number that we had, that long one, and we split those up into 4 equal segments, we get the value B, 1, E, and F. And if we do the calculation on it, F is equal to 15 times 16 to the 0, because 0 is the placeholder of that F. Then we have E times 14 to the 16 to the 1, plus 1 times 1 to the 16 squared, and plus B, which is equal to 11 times 16 to cubed. So this is equal to 15 times 1 is 15, 14 times 16 is 224, 1 times 256 is 256, and 11 times 4096 is 45,056. So if we add these 4 numbers up, B1EF is actually equal to 45,551 decimal. So that is what that actually looks like. So if we look at, again, that binary number is represented by this hexadecimal number, which actually just represents the binary, which is equal to 45,551. Now that seems really complicated, but that's the way it works, because remember, the PLC will only understand either an on or off condition. Now, if we take a look, we can, Windows has a good program for programmers when doing this kind of conversion. And it's the Windows calculator that is installed automatically when you install all Windows operating systems. So let's call up the Windows calculator. You can do that by selecting your search and search for calculator, and it will call this up on your computer. So let's call that up. There it is here. And right now I'm working on a Windows 10 PC, so you can actually see that that's Windows 10. Refer to our website and you'll see what Windows 7 looks like through the post itself of this video. So this is our standard Windows calculator. And to call up the program view, you can hit a combination of Alt+3, or you can go to the menu here for navigation, and we can hit Programmer. When we get the Programmer, we can see here that the default numbering system we have is decimal, but we also have hexadecimal, octal, and binary. So if we enter the decimal number that we just calculated, which was 45,551, you can see here under hexadecimal, it's equal to B1EF, which is the same thing we had here. Or in binary, it's 1011, 0001, 1110, and 1111, which is exactly what we see here. So all these are equivalent. We can select this to show it, and again, it just shows the other. There's my hexadecimal, and you notice here on a calculator, they've actually added these numbers here. If we go into binary, again, we can enter the binary number, and we can see what that equivalent is going to be. So again, if we hit escape, clear that off, hit 111, in binary, you can see that's equal to 15. We hit the next 3 and we'll hit 000. The next 4, you'll see that now the next hexadecimal number is 0. And then we can do any combination. 1100. We have C and Let's just do a 3. Which is a 3 at the end. So any combination, we quickly see what that equivalent is going to be in decimal for us, or octal or binary, and we can calculate any one we want now with a long way. So if you enjoyed this video, please hit the like button below. If you have any questions about the video, please leave a comment below and I'll do my best to answer it. If you want more information about us, or you want our free ebooks on numbering systems or robust data logging, please click on the link in the description below to get it. A new video is posted every Monday, so make sure you hit the subscribe button to get more videos like this in the future. Remember to click the bell beside your subscription to actually receive those notifications. Thanks so much for watching. I'll see you next time. Stay safe.